Welcome to our expert technical training on responsible AI. Today we are focusing deeply on the essential considerations for ensuring reliability and safety within your AI solutions. Welcome back to our expert-led training series on artificial intelligence. Today, we are undertaking a comprehensive deep dive into the principles of responsible AI, with a specific, laser-sharp focus on the considerations for reliability and safety within an AI solution. As you step into the role of an AI architect or developer, understanding these ethical and operational frameworks is absolutely paramount. According to our official documentation, responsible AI is a term used to describe the critical considerations for building AI systems that include strict guardrails. These guardrails are explicitly designed to mitigate the risk of harmful, illegal, or offensive content generation, as well as to prevent dangerous automated actions from occurring in the real world. To achieve this, the overarching framework outlines 6 core principles that must be embedded into every phase of the software development lifecycle: fairness, reliability and safety, privacy and security, inclusiveness, transparency, and accountability. While each of these pillars plays a vital role in an equitable system, today we are singling out reliability and safety. As we will see, AI models are incredibly powerful, but they operate much differently than traditional deterministic software. They are mathematical systems that recognize patterns and make predictions. Because of this architecture, they require a unique approach to quality assurance, testing, and operational deployment. We must build applications that anticipate errors and handle them gracefully, ensuring that end users and systems are never exposed to undue risk. Throughout this session, we will examine the foundational concepts, explore the mathematical realities of probabilistic modeling, and break down a real-world scenario involving computer vision and robotics to see exactly how these safety measures are implemented in production. From a technical implementation standpoint, introducing responsible AI guardrails means writing application logic that intercepts the model's output before it reaches the end user or triggers a downstream automated process. Your code must evaluate the generated response against predefined safety policies, utilizing content filters and threshold checks to ensure absolute reliability and safety. This flowchart breaks down the responsible AI framework, highlighting the 6 core principles and directly mapping reliability and safety to the mitigation of harmful automated actions. Let us move forward and explicitly define what reliability and safety mean in the context of an artificial intelligence solution. The most fundamental concept you must grasp as an AI professional is stated clearly in our training materials. AI is based on probabilistic models, which means it is not infallible. Traditional software applications are deterministic. If you provide a specific input, the predefined code execution path guarantees a specific, highly predictable output every single time. Artificial intelligence does not work this way. Instead, AI applications are powered by machine learning models, which are complex mathematical systems trained to recognize vast patterns in enormous datasets. When you interact with an AI application, the model performs inference, meaning it applies what it learned during training to new, unseen input in order to generate a probabilistic prediction. Because the output is a prediction rather than a hard-coded certainty, errors, hallucinations, and unexpected behaviors are entirely possible. Therefore, AI-powered applications need to take this inherent fallibility into account and mitigate risks accordingly. Reliability means that the AI system performs consistently well according to its design specifications, even when faced with ambiguous or noisy input data. Safety means that when the system does inevitably fail or encounter a scenario it cannot resolve, it does so in a manner that does not cause physical, financial, or emotional harm. You cannot blindly trust the output of an AI model. You must actively engineer your surrounding application infrastructure to be suspicious of the AI's predictions, placing robust safety nets around the core intelligence. In practice, building for reliability and safety involves implementing extensive error handling, fallback mechanisms, and validation routines within your application code. When your client application makes a REST API call to a model endpoint, the resulting JSON payload must be parsed and strictly validated. If the output violates schema requirements or contains unsafe anomalies, the code must gracefully default to a safe state. Observe this diagram comparing inputs to probabilistic inference. It clearly visualizes how a machine learning model can generate both expected outputs and unpredictable errors, necessitating strict safety nets. Understanding that AI models are probabilistic and fallible leads us directly to the engineering strategies required to mitigate these inherent risks. One of the primary techniques highlighted in the official documentation for mitigating the risk of harmful content generation is the implementation of robust content filters. When dealing with generative AI models that produce text, images, or code, the system can sometimes generate outputs that violate organizational policies or societal norms. Content filters act as an automated, highly reliable safety layer, positioned directly between the AI model's output and the end user's interface. These filters actively scan the generated responses for profanity, hate speech, violent references, or attempts to execute unauthorized automated actions. If a filter detects a violation, it blocks the content and returns a standardized safety error, ensuring the application remains reliable and safe. This process is absolutely critical because AI systems mathematically reflect their training environments. Even with extensive fine-tuning and strict system instructions, the unpredictable nature of probabilistic inference means that inappropriate combinations of tokens can still emerge. By integrating content filtering APIs alongside your core AI models, you create a defense in-depth architecture. The model is tasked with generating the most accurate prediction possible, while the independent filtering system is tasked solely with evaluating that prediction for safety compliance. This dual-layered approach is a best practice for enterprise AI deployments. To implement content filtering programmatically, developers often utilize dedicated safety endpoints or built-in SDK features that evaluate prompts and completions in real time. Your application logic should catch specific safety exception codes returned by the API. For example, if a user prompt triggers a safety violation, your code must intercept the 400-level HTTP error and return a polite, pre-programmed rejection message. This workflow illustrates the defense in-depth architecture. Notice how the content safety filter sits directly between the raw probabilistic output and the user, actively blocking any detected violations. To truly contextualize the principles of reliability and safety, let us examine a high-stakes, real-world scenario described directly in our Microsoft Learn source materials. Consider an AI-powered robotic solution that uses advanced computer vision to detect objects in a physical environment, such as a factory floor or a highly automated warehouse. In this scenario, the artificial intelligence is not merely generating text on a screen, it is driving automated physical actions in the real world. The training documentation explicitly states that such a system should avoid unintentional harm or damage at all costs. This is the ultimate test of reliability and safety. If the computer vision model misidentifies a human worker as a piece of cargo, or miscalculates the structural integrity of a delicate component, the robot could cause severe injury or catastrophic equipment damage. Because the object detection models powering the robot's vision are probabilistic, we know they will eventually make an incorrect classification. The application architecture must assume that these classification errors will occur. Therefore, the physical control systems cannot be hardwired directly to the model's raw output without an intervening safety layer. The software governing the robotic arm must be designed to prioritize human safety above operational speed and factory efficiency. We must implement strict mathematical safeguards that evaluate the AI's certainty before any physical movement is authorized. In a robotics application, the codebase bridging the AI vision service and the hardware controller must be incredibly robust. The code will receive a JSON response containing the detected object labels and bounding box coordinates. Crucially, the logic must completely ignore this payload if it contradicts physical sensor data or violates hard-coded spatial constraints, ensuring the hardware physically halts upon detecting anomalies. Here we see the critical risk point in a robotic vision system. The diagram shows how a prediction from a computer vision model, if inaccurate and unchecked, leads directly to catastrophic damage without a safety layer. How exactly do we implement these mathematical safeguards in our robotic computer vision scenario? The training documentation provides a precise, actionable strategy. One way to accomplish this goal is to use probability values to determine the confidence in object identification before interacting with physical objects, and completely avoid any action if the confidence level is below a specific threshold. Let us break down how this works in practice. When an AI model analyzes an image to detect an object, it does not simply return a definitive label. Instead, it returns a list of possible labels, each accompanied by a confidence score ranging from 0 to 100%. This score represents the model's statistical certainty regarding its own prediction. To guarantee safety and reliability, developers must establish a strict confidence threshold within the application's business logic. For example, you might program the system to only authorize the robotic arm to pick up an item if the computer vision model returns a confidence score of 95% or higher. If the model is only 70% confident that the object in front of it is a harmless box, the application must deliberately reject the prediction. The code will halt the automated process, prevent the robotic arm from moving, and trigger an alert for manual human review. This precise use of probability values and strict threshold enforcement is the definitive mechanism for transforming an inherently fallible AI model into a highly reliable and safe enterprise solution. Implementing a confidence threshold requires writing conditional logic that parses the inference response payload. Your code extracts the confidence underscore score float value associated with the predicted label. You then write an if statement checking if this score is greater than or equal to your predefined safety constant, e.g., 0.95. If the condition evaluates to false, the code throws an exception and safely terminates the execution flow. This logic flow maps the confidence threshold implementation. The system evaluates the predicted score against a 95% threshold, routing to physical movement only if met, otherwise triggering a safe halt. Establishing confidence thresholds and content filters is crucial, but these mechanisms are only effective if they are rigorously validated. The principle of reliability and safety dictates that an AI application must be thoroughly tested across an exhaustive range of scenarios before it is deployed into production. Because AI models are dynamic systems that can respond unpredictably to edge cases, traditional software testing methodologies are entirely insufficient on their own. Development teams must implement specialized AI evaluation strategies. This involves systematically feeding the model adversarial inputs, heavily degraded audio or visual files, and highly ambiguous prompts to explicitly trigger failures. By intentionally pushing the system to its breaking point in a controlled environment, engineers can verify that the safety guardrails, such as confidence thresholds and fallback routines, activate exactly as intended. Furthermore, testing for reliability is an ongoing, continuous process. As models are updated, retrained, or fine-tuned with new data, their probabilistic behavior can subtly shift. Continuous monitoring and automated safety evaluations must be integrated directly into your deployment pipelines. This ensures that any degradation in the model's accuracy or safety compliance is immediately detected and addressed, guaranteeing that the application maintains its operational integrity throughout its entire lifecycle. By proactively identifying vulnerabilities during the testing phase, organizations can prevent dangerous anomalies from ever impacting end users, firmly upholding the core tenets of responsible AI. Testing AI safety programmatically involves building automated evaluation scripts that utilize an extensive library of edge case datasets. Developers use dedicated evaluator functions to score the model's output against safety metrics. In your CI/CD pipeline, you write test assertion code that automatically blocks the deployment of a new model version if its safety scores drop below the established baseline reliability requirements. This deployment pipeline diagram shows how adversarial inputs test the safety guardrails. Only models that pass these strict reliability evaluations are deployed, while unsafe behaviors are explicitly blocked. As we conclude our deep dive into the considerations for reliability and safety within an AI solution, we must anchor these technical practices back to the overarching principle of accountability. The documentation clearly states that ultimately, the people and organizations that develop and distribute AI solutions are accountable for their actions. You cannot deflect responsibility onto a probabilistic machine learning model if your application causes harm. It is imperative for organizations developing AI to actively define and apply a strict framework of governance to ensure they consistently apply responsible AI principles to their work. This means establishing clear policies for safety testing, mandating peer reviews for threshold configurations, and maintaining comprehensive audit logs of all AI-driven decisions. Thank you for joining this advanced training session on building reliable and safe AI solutions. If you found this technical deep dive valuable, please like this video and subscribe to our channel for more expert-level content. To take your career to the next level, I highly encourage you to visit quicktechie.com for premium certification prep. We offer comprehensive Q&A banks, in-depth ebooks, audiobooks, advanced training modules, and expert interview guides designed to help you master these critical concepts. Remember, mastering the ethical frameworks of AI is just as vital as writing the code itself. By maintaining absolute transparency regarding how safety thresholds are established and enforced, teams build trust with their users and regulatory bodies alike. Stay secure, build responsibly, and keep learning. Accountability in software engineering translates to rigorous logging and auditing mechanisms within your codebase. Every time your application evaluates a confidence score or triggers a safety filter, the exact input, the model's raw probabilistic output, and the application's final routing decision must be permanently written to a secure telemetry database. This comprehensive logging code provides an immutable trail for forensic governance. Our final diagram illustrates accountability in action. It demonstrates how all threshold evaluations and safety filter executions feed directly into an immutable audit log, empowering robust organizational governance.
Welcome to quicktechie.com. So just type in quicktechie.com here. Then you can go through the material which is provided by Quicktechie. So we have first of all video courses which you can go here and you can find the various video courses across the technologies as well as finance domain. So if you see in Microsoft, we have 8 programs currently running. Next, you can go through the ebooks available. So all the ebooks which are in PDF format today, and you can download this. So let me go through Microsoft certification ebooks. You can click on any of this and you can see this is the PDF available for you to download. So these are the premium ebook mostly available on quicktechie.com platform only. Now the second part is exam simulator. As we primarily focus on the all technology companies and finance domain certification preparation material, so this is company wide listed here and you can go through this. So let me go through the Microsoft one again. You can see this is all Microsoft related certification. AB 730 exam, if you open it, so you can see here this, and all all the practice papers are available here. Today we have a 5 practice paper. So click on the first practice paper. It would load the questions. You can answer this question. This is way you can answer it and you can move to the next question. Now third material we wanted to highlight is an audiobook. So we started recently with the audiobooks as well, which you can listen on the go, and various technology wise ebooks are available. And at the last, this is our alumni. These people who are subscribing to our courses and this platform, they are all listed here. And at the end, I wanted to tell you, if you find any course or training or certification preparation material which you want to get us prepare for yourself, please put on the comment section. If you're watching on YouTube, on Udemy, or on this platform itself, quicktechie.com, then please put the comment, or you can even send an email to using this contact us options here. You can directly do the WhatsApp message. You can call us on this numbers as well.